Hello, physicists. Welcome to our January 25th edition of Physics. Today we are going to be moving into the second dimension. So before we just talked about moving back and forth along the line, today we're going to start moving around a plane. Now, on Friday, you all took a quiz, and one of the questions on this quiz was a little confusing. It said the speedometer on a car's dashboard measures which of the following? And the answer I was fishing for was instantaneous velocity. The answer that about half of you gave me was average speed. So if you gave me average speed, I gave you a point back for that. So our average score initially was an 84%. That seemed a little low to me for Friday quiz. So we got our average score up to 91. That is what I'd like to see. Okay, so a speedometer on a car obviously tells you how fast you're going. My guess is that when a number of you saw velocity, you thought to yourselves, velocity also has some component about what direction you're going in. And so if the speedometer doesn't tell me that, it can't be velocity, which is a fair point. On the other hand, average speed seems to indicate more of a longer time frame over which the speed is the distance over time is taken. But okay, I'll try to write better questions. All right, here's another question from Friday. It says, a motorcycle travels due south covering a total distance of 80 kilometers in 60 minutes. Which one of the following statements concerning this situation is necessarily true? The only one of these statements that is true is that the average velocity of the motorcycle is 80 kilometers per hour due south. Why? Well, that's the only one of those things that has to do, that is totally determined by the initial and the final points, the average velocity. So for instance, so here I went 80 kilometers. There's my x in meters. And here's my t in seconds. Okay, so if I just went straight from here to there, that would be an average velocity of 80 kilometers per hour. And it would also be a instantaneous velocity of 80 kilometers per hour, because the slope at every point would be that. However, I could take lots of different routes. I could go like this, for instance. And if I had the same initial and final point, I would have the same average velocity. But in this case, I would be going forward, backward, forward, backward, forward, backward, forward, backward, sort of a 2 steps forward, 1 step back type of arrangement. And I would have a higher speed at every point along that path, because I would be going faster. I mean, I guess not there. I'd be turning around sometimes. At those points, my speed would be 0. But my average speed would be much higher than the average speed in the case where I just went straight from one point to the other. So the only point I'm trying to make here is that lots of different stories can be described by the same crude measurement, but in this course we will be sort of focusing on sort of simple situations. All right, now here's sort of our plan for the next 2 weeks. This week we're going to talk about how to describe motion in 2 dimensions, x and y, not just x now. And next week we're going to review, and by the end of next week I'm hoping for us to have our first exams. That's not this week Friday, that's 1 week from this week Friday, so about 2 weeks from now. So I thought, to get us into this, let's go ahead and just quickly review everything that we've done so far, and then introduce our new thing for today, which is the idea of vectors. So on our very first day of class, what did we do? We learned about unit conversions. So for instance, I can always multiply by 1 if I have 5 feet, and I want to connect that to inches. I can take 5 feet times 12 inches over 1 foot, and that would give me conversion from 5 times 12 inches is the same as 5 feet. Okay, and in the case where you have feet cubed or something like that, or feet cubed per minute, so you know how quickly a swimming pool is draining or something like that, you have to sometimes use multiple copies of that one. So for instance, if I have a feet cubed, I've got to have a cubed on the bottom and a cubed on the top to give me the relationship between feet cubed and meters cubed. And I also, if I wanted to transform the time units, I could do that too. All right, so you can always multiply by 1. That's the big idea there. The other big idea is one that we've already talked about a little bit, which is that average velocity just depends on the total displacement and the total time. So if I know where I started and where I ended, and I know how much time that took me, I can always find my average velocity, not necessarily my average speed though. Now, if I have a constant velocity, I can write that equation very easily. So here's my time, here's my x, and it's just a slope that does not vary. Wherever I start out here is my x naught. Wherever I end up at some time t goes along with that position. Okay, and so the way that we think about this in the light of our constant acceleration model is that this is just one where a equals 0. So if our speed and our velocity are not changing, that term drops out and we just go back to a simpler model. Then last week, Wednesday and Friday, we tried to work on the constant acceleration model. Remember, position you measure in meters. That just tells you where are you. And velocity you can get from the time derivative of position versus time. And this is in meters per second. It tells you how much space you're covering per unit time. And then acceleration is how your velocity is changing per unit time, so it has units of meters per second squared. And we have 3 basic equations for this, one for the position versus time, one for velocity versus time, and then the acceleration versus time is just not changing, so that is a constant in our equations. And so, since we basically have 2 independent equations, we can have 2 unknowns and always solve for the rest of the dynamics of the system. One system that we're very interested in and that we're going to continue to study is that of a projectile. And here's the simplest example. This is a one-dimensional projectile. It's just going up, slowing down, then coming back down. Now, I want to point out that this situation, if you look at the position versus time graph of it, looks like a thrown ball. But in fact, this is not getting thrown, it's just going up and down. The reason that this axis is stretched out is that that's the time axis. And so the slope of that will give you the velocity versus time. Where the velocity versus time is 0 is right at the top of the trajectory, where it's turning around, goes to the very top, stops, turns around. And notice that at the very top, sometimes people like to think that the acceleration is different when it's turning around, but if you look at the velocity versus time graph, that is not the case. The acceleration is constant. The slope of the velocity versus time graph is constant. but that does not mean it's just moving in a constant way. It means that the change in the way that it's moving is constant. So that's a distinction that sometimes can be hard to appreciate until you've used this model a lot. Now today, as I said, we're going to try to take another step. We're going to step toward moving around in 2 and 3 dimensions instead of just being locked onto just one number line. So today we're going to introduce a new math thing. And this is the distinction between a scalar and a vector. And a scalar is the type of quantity that we use when we don't have an associated direction. So think about just a number. So for instance, here's a graph of the average temperature throughout the world. It's hotter around the equator than it is at the poles. You all know this. And we don't need a directional number to capture that. Temperature is just measured by a thermometer, which gives you a number. On the other hand, if you're thinking about something like wind velocity, that has a number associated with it, which is the wind speed. But it also has a direction associated with it. You know, wind could be going east to west, west to east, north to south, whatever it happens to be. And so this we would think about as a vector quantity. We use vectors to describe quantities that have an associated direction of flow. So this is just having a number. On the other hand, a velocity has something like a pointer. And so an interesting side note that we won't need to use, actually not until next semester, is that sometimes you can use a scalar field to describe a vector field if you take a derivative of it. So sometimes the slope of a set of numbers can give you a vector. And that's how the electric potential works, for instance, to give you the electric field. But let's not go there yet. Okay, now, as I said, we want to think about vectors as pointers. And so let's try to draw one of these pointers on an XY plane. Okay? Now, I think in calculus you do this, but if you don't, let's make sure that we all are on the same page. This is our x-axis, and this is our y-axis. And we like to go between the description of x and y as Cartesian coordinates and as polar coordinates. So for instance, let's say that I have a vector. As I said, this is just a pointer. And I describe this with some r and some theta. Well, I can always go back and forth. If I use this as my 0 degrees, this as 90 degrees, this is 180 degrees, that's my minus x-axis, and then this is 270 degrees. Alternatively, we're going to go back and forth between degrees and radians. Remember, pi radians is 180 degrees, so you can make a factor of 1 out of that to do unit transformations. This is, again, just 0. This would be pi over 2. This would be pi. And this would be 3 pi over 2. This could also be 2 pi because it wraps around. Okay, now, if you have this, you'll remember some stuff from your trigonometry. For instance, opposite over hypotenuse gives you sine of theta. Adjacent over hypotenuse gives you cosine of theta. And opposite over adjacent for a triangle set up like this gives you the tangent of theta. So those are numbers that you can stick into your calculator. Of course, you need to really be careful, and it's on you. It's your responsibility to know how your calculator works well enough so that you can be sure that you're putting in the right units. So if you put in pi, let's say sine of pi should give you 0 if you're in radian degrees, but sine of pi will not give you 0 if you're using degrees. In fact, it will give you something right around 3.14. I take that back. It's going to give you 3.14 divided by divided by 180 times pi. Okay. Anyway, now if you want to make that the transformation between these two, you can use x equals r cosine theta and y equals r sine theta. And if you use the way of putting degrees from 0 all the way to 360, or from 0 to 2 pi, depending on whether you're using radians or degrees, this setup will get you the right signs every time. So here you have both x and y are positive, here you have x negative, y positive, here you have x negative, y negative, here you have x positive, y negative. This setup gets all of that already. It should already be figured out by your calculator, no problem. Okay, so that's a nice thing to remember. Now, as I said, if we have our vector written as an angle and a magnitude, the magnitude is the length of the vector, then we should be able to split it into its components. So here we go. Ax is a times cosine of theta. Ay is a sine of theta. And we can also go backwards so that if we have that magnitude, we should be able to find the magnitude and the angle. We should be able to find the if we have the x and y components, rather, we should be able to find the magnitude and the angle. The only thing I want to caution you about a little bit is that, for instance, if you use tangent of theta and you use ay over ax, and you're in the first quadrant, ay and ax, and you just plug in the numbers. You wanted to get the theta equals, and then you'd go, and on your calculator, you should have an inverse tangent, tan to the minus 1 of ay over ax. That'll give you the right answer, okay? However, if you go ahead and go, for instance, into this quadrant here, the second quadrant, then your ax would be negative. So you'd be taking the inverse tangent of something negative. The angle that you get then is going to be negative, and it's going to be between negative pi over 2 and 2, negative 90 degrees and 0. And so that can't be right. So my suggestion to you is always just to draw a triangle and remember that here's your angle, here's your opposite over adjacent, and you can always find this angle, and then drawing it on your xy coordinate, you can use that to figure out where on 0 to 180 you're actually at, or 0 through 360 that you're actually at. Use the a proxy angle. So that's going to be tangent inverse of opposite over adjacent. You'll find some angle, and then you have to look on this to figure out how it exists between 0 and 360. So here's an example of what I mean. This is an example from your book. Here's figure 310 out of chapter 3. It says a small airplane leaves an airport on an overcast day and is sighted later 250 kilometers away in a direction making an angle of 22 degrees east of due north. This means that the direction is not due north, directly to the north, but is rotated 22 degrees to the east from due north. How far east and north is the plane from the airport when it is sighted? Well, the situation they're telling you about is something like this, where you have 22 degrees. Now, obviously, these two angles have to add up to 90, so then this would be 68 degrees. So if you just wanted to use this and say this is the length of this vector is 215 kilometers, I can resolve that into, this would be north and this would be east. North and east components, effectively the y and the x components, using my standard trick of taking 250 kilometers times cosine of theta to get my x component. But I needed to make that little change so that this is 68 degrees rather than 22 degrees. So that's the thing, that's just the sort of notational issues you always have to be on guard for when you're setting up these types of problems. Here's a homework problem that I gave you. The homework is on Canvas, by the way. If you have not handed in your homework today, remember, you don't get a penalty until Wednesday. So please try to get it in by class time on Wednesday. But I would definitely start getting going on this homework 3. Here's a homework example. You have the x component of vector A is minus 25 meters. Okay, let's draw it. Here's our x. There's our y. X component is minus 25 meters. And the y component is plus 40 meters. Okay, so minus 25 plus 40. So I've got some arrow pointing out from the origin. What is the magnitude of A? Okay, well, you're going to just use your Pythagorean theorem. Okay, you're going to use your 25 squared plus 40 squared and take the square root. And then you're going to find out what is the angle between the direction of A and the positive direction of X. So that's this angle. All right? However, I suggest that you find that angle. Let's call it prime. So the tan theta is going to be the opposite, 40, over the adjacent, 25. And then you can find out what that theta prime is by using your inverse tangent function on your calculator. And then this whole thing is 180 degrees, and so you're going to take 180 minus that piece, and that should get you where you need to go. Okay, so that's the sort of problem that I've given you in the homework to sort of puzzle over and make sure that you're clear in your head on how these vectors work. Now, when I add and subtract vectors, another piece of complication comes in, but it's really not that bad. So let's draw a picture. Let's say I have one vector here, let's call it A, and then a different vector pointing maybe like that, and we'll call that B. Now let's say that the first one of these represents the displacement that our young scholar takes in the morning, and then the second one it represents the displacement that our young scholar took in the afternoon, and we're interested to find out what the total displacement of our young scholar is. Well, one way to do it would be to add up these two vectors. How do I add it? Well, if he went like this at the beginning, that's the morning, and then like that in the afternoon, that gives me some final vector where C is going to be A plus B. Okay? So if I'm adding A and B, I could have added B plus A. That would have been going to add that plus this, and it would give me the same thing. But effectively what I'm doing is this. I have a vector A that has two components, AX and AY. And I have some vector B that in this picture has two components, BX and BY. And if I want to add them together to get that new vector, that's C, I would use C equals AX plus BX and then AY plus BY. Okay, so the rule for adding vectors is that you just add the components. If you know what the x component and the y component of A is, and the x component and the y component of B is, you can find out what the x component and the y component of C, their vector sum, is. Notice you can also do this with subtraction. So for instance, let's say that I have two vectors, A and B, and they represent the positions of two different people. And I want to calculate how far my person at point A would need to, or what direction they would need to go to get to point B, or something like that. Then I could also use this, which would be B minus A. Okay, so sometimes you're also going to want to use vector subtraction. And it goes the same way. You just have all the components of B minus all the components of A. So BX minus AX, comma, BY minus AY. And that would be your vector. All right, here's a nice example. Pay no attention to the raven attacking the eagle. All right, so there's the y-axis, there's the x-axis, and it says this. A person walks in the following pattern. So let's mark this as north, never eat shredded wheat. Okay, north, east, south, west. They go 3.1 kilometers north, then 2.4 kilometers west. Okay, so I'm going to draw that as a vector. And I'll draw that as a vector. 2.4 kilometers west. And then 5.2 kilometers south. So we're going to come back down, overshoot, and keep going. Okay, so this is 5.2. Okay, sketch a vector diagram that represents this motion. I think we pretty much did that. Let's write those three as sort of an A, B, C vectors. We could write them as this first vector is all in the y direction, not at all in the x direction. So our x direction would be 0, and my y direction would be plus 3.1 kilometers. My second one would be this one. Now, I'm going in the minus x direction and not at all in the y direction, so then that one would be minus 2.4, comma, 0. And then for my third vector, I'm going down, or rather, south, and that's in my minus y direction, and so that would be 0, comma, minus 5.2. Okay? And so if I want to find this final vector, all right, this is my A plus B plus C, then that would just come about by my adding all of the x's, 0 plus minus 2.4 plus 0, that would be my x component of this new vector. And then 3.1 plus 0 plus minus 5.2, that would be my y component of this final vector. And then once you have that, it asks how far and in what direction would a bird fly in a straight line from the same point starting to the same final point. Well, in that case, you're going to just use your, if we call that d, you're going to have your dx squared plus dy squared. And then this is some sort of a triangle, and I would go ahead and find that angle, and whatever that angle is, you're going to have to add 180 degrees or pi degrees to it to get your final angle. Okay? Or maybe you could just find that angle and say, you would go, theta prime degrees south of west, something like that. All right. Now, this is our last, sort of our last thing that you're going to be using in your homework. There are two ways that your book writes vectors. Okay, so I showed you the way where we have a and you write it with like a brackets like this, where you have ax, ay, az. Another way that you can write it is in the notation where you have a vector times a scalar. So this I, you think of that as a little vector pointing along the x direction. This j, you think of as a little vector pointing along the y direction. If you have a k with a hat on it, that would be a vector pointing along the k hat direction, which is the z direction. So one way of writing the vector is in component form like this. Another way is to write it in this kind of vector times scalar form, which would be ax times I plus ay times j plus az times k. Okay, so in this way, you think of this as also representing a vector as a sum of three vectors, and these are all perpendicular, so all of your Pythagorean theorem stuff would work really nicely with those. So that's sort of just two ways to represent. Here's a nice homework problem that shouldn't be too bad. It says in unit vector notation, what is the sum of A? I'll put a vector and B, put a vector hat on it. If A with a vector hat and B with a vector hat are those. What are the magnitude and direction of A plus B? Okay, so to find A and B, you're going to say A plus B equals, and you can even, you can write it in IJ notation, or you can have like 4 plus minus 13, and that would be your first number, and then 3 plus 7, that would be your second number, and then you can use your Pythagorean theorem and your trigonometry to find a magnitude and an angle. Okay, so what I would like you to try for this Wednesday, one more thing. Okay, so later on we're going to do a whole bunch of stuff with vectors. Sometimes it makes sense to rescale vectors. So here's, for instance, if this is your original vector and you took it times 1.5, that would just make it longer, but in the same direction. Or you could take it times 2, that would make it even longer in the same direction. You could take it times 0.5, that would make it shorter, but still it would retain its the direction that it's pointing. Later on, we're going to learn how to take vector products. Here's something called the dot product, where if you have two vectors, A and B, you could take AX times BX plus AY times BY plus AZ times BZ, and it turns out that you can relate that to the angle between your two vectors, okay? And then we will also learn about something called a cross product, which we'll use a lot when we are talking about angular momentum and things like that. And the nice thing about that is that you start with one vector and another vector, and it gives you a third vector that's perpendicular to the first two, and the size of it tells you something about the angle between the two. So I don't want to burden you with those right now because I think this is plenty for one day. And what I would like for you to work on for Wednesday is just try these homework problems. So the whole first page of your assignment this week is just Chapter 3 stuff. And so that's what I would like you to go home and try to do after you watch this. Okay, so our big ideas of today. Vectors are helpful tools for expressing physical quantities that have magnitude and direction. You can imagine that we are going to use this for quantities, for instance, like a velocity. And so when we shoot off our rocket, we're going to have an x component to the velocity and a y component to the velocity. And so we're going to have to work out exactly how that works next time. Vectors can split into components using trigonometry, x, y, and z components, and those can be helpful because they allow you to add vectors together. And you can do it as geometrically, where you're putting the tip of one to the tail of the next, and then going from the tail to the tip of the new. Or you can do it just algebraically by adding all of the x components, all of the y components, all of the z components. And so those are two ways to understand the process. All right, so next time we're going to use this to start working on two-dimensional projectile motion. Okay, so stay tuned and good luck.